Hello, I am Manjil Saikia. I am a faculty member in the School of Arts and Sciences associated with the Mathematical and Physical Sciences Division. I am also the major advisor for the Mathematical and Computational Sciences major and also the minor advisor for the minor in Mathematics. So this is an introduction to the course MAT431, Algebraic Combinatorics. We offer this course in the winter 2025 semester for the first time. This is a 3-credit course and I'll be the instructor for the course. So let's move on to what the course is, and I'll give an example of the type of problems that we study in this course. First, let us start with what is combinatorics, which is the second word in the course title. Combinatorics, very simply, is the science of patterns and arrangements. And by patterns and arrangements, we mean things such as sequences of length n consisting of only zeros and ones, which you probably know as the binary sequences. Or it could also be the number of ways of arranging 10 boys and 10 girls in a circular fashion, such that no two boys are sitting together and no two girls are sitting together. So it can be a variety of different things, and we'll study some of these combinatorial objects. Combinatorics essentially deals with the study of existence and the number of arrangements possible for any given mathematical structure. Algebraic combinatorics, which is going to be what this course is about, uses techniques which come from algebra to study combinatorial problems. Our main goal would be to study certain combinatorial objects, but the techniques that we're going to use while studying these combinatorial objects will be coming from either abstract algebra or from linear algebra. Now, what type of problems we are interested in and how does algebra come into the picture? For that, let me show you a puzzle and I'll give you the partial solution to this puzzle. So consider this very odd town where you have n people and they form clubs in such a way that every club has an odd number of people, while every two clubs have an even number of people in common, and that number of people in common could also be 0. Now the question is, what is the maximum number of clubs that can be formed? If you think about this for a while and if you do some experiments using pen, pencil or even a computer, then you would see that the clubs can be at most n, which is also the number of people. So how does one prove this type of result? Remember, there are 3 conditions. First condition is that the town has n people. The second condition is that each club should have an odd number of people. And the third condition is that any two clubs can have only even number of common people in them, and that even number can be 0. So I already said that the answer is n, and what about the construction? So one construction which comes to our mind would be that each person forms their own club, and you can see that all the 3 conditions are satisfied: n people, n clubs. Each club has an odd number of people in it, which is 1, and no two clubs have any common member. So that means the number of common members between any two clubs is 0, which is an even number. Now we prove that we cannot do any better. So we cannot go from n clubs to n plus 1 clubs. And the way to prove this would be using some amount of linear algebra. So what we would do is we just number the people 1, 2 up to n, and we'll suppose that we can form m clubs, and we'll number the clubs as 1, 2 up to m, and we associate to each club a characteristic vector. So if you have done linear algebra, you know what this characteristic vector would look like. So these would be all zeros except for the entry, jth entry would be 1 if vi is, if the jth person belongs to club I, and it will be 0 if the jth person does not belong to club I. We can prove that if you take the dot product of this vector vi with itself, then the answer is 1. And if you take the dot product with a different vector, vi dot product vj, then this will be 0 for any I not equal to j. We want to show that m, the number of vectors, cannot exceed n. The number of vectors would give us the number of possible clubs, and this is what we want to show. And this can be done, and it will be done in the course. It is actually one of the first examples that we'll pick in the course, and it is not very difficult. However, the main point of this slide is not the solution, but this idea that a purely combinatorial problem, when recast as an algebraic problem, is sometimes easier to solve rather than trying to do it by brute force or by hand. I'll leave you with one more puzzle which we'll discuss in the class. So this is called the 100 prisoners problem, And the setup is the following. So there is a prison and there are 100 inmates in that prison who are on death row, and they are numbered from 1 to 100. Now the director of the prison or the jailer of the prison gives them a last chance, and the chance that they give is the following. So he calls the prisoners to a room, and the room has 100 drawers, and the director randomly puts one prisoner's name in each drawer. So each drawer will contain one name, and that name will be of one of the prisoners out of these 1 to 100 prisoners. Now the prisoners are allowed to enter the room one after the other, and each prisoner may open and look into 50 drawers in any order. So they can pick the first 50, or they can pick the last 50, they can pick the even numbered drawers, they can pick the odd numbered drawers. Only condition is that they are allowed to only pick 50 drawers, and the drawers are then closed after they open it. Now if during this search every prisoner finds their number in one of the drawers, then all prisoners are pardoned. Okay? This has to be true for all the 100 prisoners. If even one prisoner does not find their number, then all prisoners die. Very simple. So 100 drawers, each drawer has a name or a number, and each prisoner enters the room and looks at 50 drawers in some order, and if they find their number or name in that drawer, then it's all well and good. If they are not able to find, then all prisoners will die. Before the first prisoner enters the room, the prisoners may of course discuss some strategy, but they may not communicate once the first prisoner enters the room. Okay? So this is the setup. Now the question is, what is the prisoner's best strategy? So it might look like a very difficult problem, because if you think naively, then you would see that probably the probability of each prisoner finding its own name is 1/2 to the power 100, because 50 drawers out of 100 drawers, so half 1/2, and each prisoner gets the chance, so 1/2 multiplied 100 times, which is a very minuscule probability of finding the name or the number. However, there is a strategy which guarantees that the prisoners will be successful at least 30% of the time. And we are going to discuss that strategy as well in the course, but for now you can think about this problem, and if you find a truly nice solution, then you can of course write to me via email. Some course information before I leave you. So this is a 3-credit course, and the prerequisites are as follows. So you need to do at least one of these 4 courses. Either you can do MAT 101 discrete maths, or you could have completed MAT 248 applied linear algebra, or MAT 312 abstract algebra, or MAT 315 combinatorial enumeration. So please note that only one course would suffice. You don't need to do more than one course out of these 4 courses. This is going to be a major elective for the mathematical and computational sciences major, and this is also going to be a minor elective for the mathematics minor. So that's all from me. See you next semester.